Today, we're solving problem 25 from the Fall AMC 10B from 2021. Okay, a rectangle with side lengths 1 and 3, a square with side length 1, and rectangle R are inscribed in a larger square as shown. The sum of all possible values for the area of R can be written in the form m over n, where m and n are relatively prime positive integers. What is m plus n? And this is the drawing they gave us in the test. So what they're stating is that this rectangle has a side length of 1 and has this length of 3. This is definitely not drawn to scale. And this square is supposed to have side lengths 1 and 1. Well, you get the idea. Square is, a square. Now, we want the sum of all possible values for the area of R. This is R. I forgot to model it. But we want the sum of all possible areas of R. That means there could be one area, there could be like 2 areas. We don't know how much. But it can be written in the form m over n, where m and n are relatively prime positive integers. We want to find the sum of them. So for this problem, what we're going to need to do is we're going to need to draw some lines here, and we have to use the properties of right triangles to solve this problem. Once we draw a couple of lines, it looks like this. And the reason why we do this is because we want to form congruent triangles. Take this one for example. We form this one to make a congruent triangle like so, because this length is 1 and this length is also 1. Therefore, it's an isosceles triangle. When we cut it in half from the height, these two are equal. And we can also construct the same type of triangles that are equal to it. Okay, and we also construct this line to separate it into 2 triangles to make it easier to solve for. Okay. Well, now we can start using variables to represent the height and length of the triangles. Let B be the height, and let A be the width. This is B and A. This is B and A. This is B and this is A. This is B and this is A. And this is B. Okay? Well, now let's take a look at something else. The scale factor. So we see that this triangle is a similar triangle to these smaller triangles. I'm not going to do a rigorous proof, but basically these angles have the same measures in these triangles, so we can prove that they are similar. Okay, this hypotenuse length is 3. This hypotenuse length is 1. The scale factor of that is 3. So this is going to be 3b, and this is going to be 3a. Knowing that this is a square, we can set up an equivalent equation to solve for one of the variables. So we sum up all of these on this side, and then sum up these on this side. So 3a plus b plus a. Well, it's a square, so we can make it equal to 3b plus a. A's cancel. This becomes b. These cancel. We get 3a is equal to b. So we can now replace every b in terms of a, and this will make it a lot easier to solve for. Okay, once you've changed every b into a 3a, it should look like this. And there's one thing I ignored, and I just realized. This side length should be a b, so we can write 3a. Okay, now we want a new variable for this length that we can use. We don't want to use a singular variable. We want it in terms of 3, since this is also a term of 3. So let's go for 3 times c. Okay. Well, we want this side length to sum up to 10a. This is 4a here. We want 6a here. So we can do, to make a 6a minus 3c, and it's already being added back here, so that cancels out. This is 3a, This is going to be 3b. And this is going to, no, this is going to be 3c, sorry about that. And this is going to be c, because we can also set that equal to it. This is the whole reason why we did it. This is 1c, this is 3c, etc., etc., etc. It's in that way where we solve for it. We can do the same thing here. This is 6a, we want a 4a, so we get 4a minus c. Now we want to solve something preferably we want to solve for something here, preferably c. We can do that by setting up an equivalent ratio. 3a over 3c, the 3's cancel out. This is going to be, this is going to be 6a minus 3c over 4a minus c. Okay. Now we can multiply these out. So on this side we get 4a squared minus ac. This is equal to 6ac minus 3c squared. Okay. We can move these over to one side, then possibly factor it. So we get 4a squared minus 7ac plus 3c squared is 0. And we can factor it into what looks like 4a minus 3c times a minus c is 0. Yes, that is correct. Now we have two possibilities here. The first case is where this is equal to 0. So 4a minus 3c is equal to 0. That means c is equal to 4/3 a. The second possibility is where a minus c is 0, c equals a. Okay, now we can use the Pythagorean theorem to solve for these side lengths, and then we'll get an a squared at the end, so we can solve for the value of a squared and then add up all this areas and get our answer. Now some people might begin to panic at this point because you get two answers for c, but the problem said that we want all the values, all the areas summed up together. Let's go with the first one. The first one, well, let's just solve for this hypotenuse here. I won't go into details, but the first one is going to be 5a. Because this is a 3, 4, 5 triangle. Then this is going to be 10/3 a by using Pythagorean theorem. So the area is going to be 5a times 10/3 a, or 50/3 a squared. Now this one, when c equals a, both of these lengths are 3√2 times a. So when they're both of them, you just square it to get the area. This is 18a squared. Now you can actually find a squared by using the Pythagorean theorem. We don't want to solve for a, just a squared. We can take one of these small triangles that we made earlier with a hypotenuse of 1, height of 3a, and length of a by applying the Pythagorean theorem. So 10a squared, this is equal to 1. A squared is 1/10. Now we can plug that value of 1/10 in, then add these two. 50/30 plus 18/10. When simplifying this, you should get 52/15. So our sum, or our answer, is going to be the sum of these two numbers. 52 plus 15 is our answer, 67. And we are now done.